Hello, hello. Okay, I hope. Okay, okay. I'll just wait for 2 more minutes. For anyone to join. Okay. Uh, let's start with week eight. Week eight. Live session. Yeah. So this. Yeah. This is Sai Dinesh Kancharana. I am the PMR of NPTL TA for Digital Signal Processing. E33. Welcome to week 8 live session. So here I'll be talking about week 8 topics, mainly the magnitude response. Okay. So yeah. Week 8 live session. So here we'll be considering systems with rational transfer function. Okay. And for a system to be stable, the ROC should include the unit circle, right? And then we also need causal systems. Okay, so here we'll be talking about stable and causal systems. Okay, so causal systems meaning that the ROC is right side outwards from the outermost pole. So ROC is mod G greater than some mod A. A is the outermost pole. I mean, I'm talking about the right sided sequences. Okay, and then some important frequency responses that we'll be talking about are the are one low pass filter, and then two high pass filter, band pass filter, and finally band stop filter. So these are the important frequency responses that we will be talking about. The one is the low pass filter, meaning the system only passes the low frequencies, that is in and around 0. And then the high pass filter are the filter which passes only the high frequencies, that is around pi. Okay, considering, so it is repeating, the DTFT repeats over minus pi and pi, so the high pass filter is the frequency around pi's. So band pass filter is when the center frequency omega is somewhere in between the low pass and the band pass, and band stop is for the particular band that we would want to reject. I mean, there the frequency response is almost 0. Okay, so these are the 4 types of frequency responses that are really important, and we will be focusing on them. Okay, and then so now stable means that ROC, so stable means mod G equal to 1 belongs to ROC, right? So then, so here Z will be some R equal to 1 e power j omega belongs to ROC. Then, so if we replace Z by e power j omega, we get H e power j omega, which is the frequency response, which is the frequency response that we are interested in. Okay, now the ideal filters are actually the one important thing is that fact is that the ideal low pass filter and high pass filters have impulse response that are non-causal. Okay, yeah, so this brick wall filters, as they are called, so ideal filters is when low pass filter, for example, passes the band until omega c. So from 0 to omega c it is 1, and then from omega c to pi it is 0. So these are like ideal LPF is somewhat like pi 0 and omega c. Okay, cheaper omega of a LPF filter. So these are called the brick wall filters. Okay, and these cannot be realized because they violate the Pale-Weiner theorem on realizability. This is what we have discussed in the previous class. Actually, we have done an example on the Wiener theorem, right? So violate the Pele Wiener theorem of realizability. Okay, so then now we will talk about, so we will restrict to the systems of classes whose input output relation, so we will restrict to systems with LCCD, right? And so these have a rational transfer function. Okay, so consider a system with LCCD equation as yfn, sorry, LCCD yes, yfn equal to equal to sigma minus k equal to 1 to m ak y of n minus k plus k equal to 0 to, that is m, and this is m, so bk x of n minus k, right? So if we do the z transform, this will result as y of z zk y of z into z per minus k, sorry, yeah, okay, let's directly, I'll skip all the steps and I'll just directly write it as h of z is equal to y of z by x of z is equal to k equal to 0 to n bk z per minus k by 1 plus k equal to 0 to m ak z per minus k, right? So this from the z transform of the LCCD equation, right? And then we can split them into the poles and zeros. I mean, we can find the poles and zeros of the numerator, and the zeros are the roots of the numerator and the poles are the roots of the denominator, and then write it in the pole 0 format, where k equal to 1 to m 1 minus zk z inverse, where zk's are the zeros, by pi of pi k equal to 1 to n 1 minus pk z inverse, where pk's are the poles, right? So here we have b naught z power m minus n z minus zk, so this is product pi z minus zk by pi of z minus pk. So these are either the trivial poles or zeros depending on the sign, right? So once we have h of z, and then let's assume that this is a causal and a stable system, then the ROC, so the unit circle also is included in the ROC, right? So then we replace z by e power j omega to get the frequency response of h of z. So h of z at z is equal to e power j omega is equal to b naught e power j omega n minus m pi k equal to 1 to m e power j omega minus zk by k equal to 1 to n e power j omega minus pk. Minus pk. Okay, so this is a transfer function in the frequency domain, and then this actually is a complex value with magnitude e power minus e power j omega, complex function, and then e power j times the angle of h e power j omega. So this is the magnitude response, right? So the magnitude of e power j omega is equal to mod b naught times, so the magnitude of this part equal to 1, so that is omitted. Meaning that the magnitude response for the the contribution of the trivial poles or zeros to the magnitude response is actually does not contribute to the magnitude response. And then what we have is b mod b naught pi times k equal to 1 to m e power j omega minus zk by k equal to 1 to n e power j omega minus pk, right? pk. So this is actually a function of omega. So this numerator is a product of the distance of the zero from, so this e power j omega minus zk mod is the distance of the excuse me yeah, so this distance of zk of the 0 zk from the point on the unit circle, so from that particular omega, right? From e power j omega for all omega yes. And then similarly the pole e power j omega minus pk is the distance of the pole pk from e power j omega, that is, so let's say we have a particular pole 0 plot, right, of this kind. Okay, let me just make this bigger. Oh no, okay, I'll just do it again. Okay, so this is the pole and this is the 0, let's say. So let's say this is the omega naught sum, so these are the values that we are talking about. Okay, so yeah, so if the 0 is actually closer to the unit circle, right, so let's say, so if 0 is closer to the unit circle, meaning the distance of that 0 from the point which is closest to the 0, on the unit circle which is closest to the 0, is actually very less, right? So let's say this so let's say this point, so here this distance is actually 0, close to 0, right? And also, so in that case the numerator of the magnitude response is decreasing, right? So if 0 is close to the unit circle, then it causes attenuation, because numerator of the transfer function is decreasing, right? Similarly similarly for the pole, there is a gain because your denominator is decreasing. Right? So basically we say that 0 provides attenuation and poles provide. So 0 provides attenuation, poles provide gain, right? So this is the takeaway that we got from here. So if 0 if so wherever there is a 0, the omega which is closest to zk, to the 0, at that omega there is an attenuation because the numerator is reducing. Similarly, when there is a pole, the omega which is closest to the pole has very less distance, meaning that the denominator is reducing, meaning there is a gain in the magnitude response. So that's why we can say that 0 provides attenuation and poles provide the gain. Okay, so let's see a few questions, right? So yeah, and then there is one more thing where, so the FIR filters actually here, but FIR filters do not have poles, right? Here both zeros and poles so like the zeros shape both passband and stop band. Okay. Excuse me. Alright, so now week 8 assignment, let's see. So I think 23rd March, right? So today is 21st March. Okay, so the FIR filters, in FIR filters, poles govern stop band behavior. So we just talked that in FIR filters there aren't any poles basically. So in the FIR filters, both zeros actually govern the stop band and the pass band behavior. Okay, yeah, so just write it down. So in FIR filter, poles govern stop band. So if we take the transfer function like a rational LCCD, the transfer function that we get from an LCCD, h of z is equal to 1 to m b k z per minus k by 1 plus 1 to n a k z per minus k, but for FIR n equal to 0, right? So there are no poles. Okay, yeah. So next is question 2. System's input output relation is given by so and so, where a is less than 1, between 0 and 1. The magnitude response is given by this thing. So basically we have an input output relation and we want to find the magnitude response. So this is actually pretty straightforward, right? So the input output relation is given by y of n equal to a times y of n minus 1 plus b times x of n, right? So we do the z transform. So for y of n, let's say y of z is a z transform, so then y of n minus 1 will have a times y of z into z inverse plus b times x of z, assuming x of z is the z transform of x of n. So y of z by x of z will actually become b by 1 minus a z inverse, right? So now you have the, so this is equal to h of z. So h of z is equal to 1 by 1 minus a z inverse. Then now we need to find the magnitude of that, right? So let's say this actually has h e per j omega is 1 by 1 minus a e per minus j omega. Let's do it. So 1 minus 1 by e per minus j omega by, sorry, it's actually b b b b. Okay, now we need to find the magnitude of this. B by 1 minus a per minus j omega. So this is actually what you want to find, right? So I think this is pretty straightforward, like, and you have a complex number, so this e per j omega per minus j omega can be written in terms of cost terms, or when you can do the rationalization and all that and find the magnitude response. So fine, so I can't found the full solution anyway, so find the magnitude response. Okay, now actually let's talk about another thing where we talk about the response of a single pole, single complex zero or pole. I mean, we'll talk about both, right? So let h of z is equal to 1 minus r e power j theta z inverse, right? So the magnitude of h e power j omega whole square is, basically if you solve this, we get 1 plus r square minus 2r omega minus theta, right? And then we usually talk about it about the magnitude response, and then find 20 log mod of h e per j omega, right? So equal to these two are the same, right? So we are talking a bit about it in the dB scale now. So now let's say the angle is theta. The angle is the angle of the 0 is theta. So at theta actually there is a attenuation, then there is a wide peak later. So let's do it once again. Right. So there is a narrow peak, and then narrow, then this is wide. So wide peak and narrow valley. So this is the response of a system, magnitude response of a system with single complex 0. So for a single complex pole we have h of z equal to 1 by 1 minus AC inverse, right? So this actually has a negative, I mean if you do the modulus and then you do the log magnitude, it will be similar to the negative of it, right? So so let's say the angle of the pole is theta, and the response will be, let's just do it again. So it will be narrow response, and then valley is broad. So wide valley and then a narrow peak. So this is the response for the single 0 and single pole. So this is actually really important. Oh, sorry. Yeah. This actually is really important. So the 0 and these poles are actually really important, because whenever we have a pole 0 plot, we know, because due to the locations we can, so basically it's like summing up, you can simply like take the responses of the individual single pole or single 0 system, and then for the whole 0 plot you just sum them up, and then you get a final magnitude response, right? So and then this again of course depends on the valley and the peak. So based on these pole 0 locations, we find the response of the system to a single pole at a time, and then you can just sum them up and finally get the final magnitude response, right? So then we recall that poles near the unit circle. So we see that this pole actually produced a peak, and then the 0 actually at the angle theta produced the value, which is an attenuation, and then again here it produced a peak, right? So again, as we stated earlier, poles near the units, poles near the unit circle boost the frequency response, and zeros near the unit circle attenuate the frequency response. Okay, I mean, yeah. So if you see the low pass, so let's talk about generating a low pass filter with a single pole or a zero. How do we do that? So we want the system to have a high gain at the low frequencies and then low gain at the higher frequencies, right? So there are two ways with the pole. Right, this, and then okay, this is this is the pole, right? So a pole, and then we have one more is a zero here. Sorry, I did the reverse. Okay, let's see. Can you tell me? So we need. So let's say we have only a single pole to place, and then we need a low pass filter. Where do we place that? So since we need a high gain at the lower frequencies, we put a place we place the pole at a lower frequency. So let's say we have a pole over here, then actually, sorry, this so because of this pole, this actually produces a narrow p. Right, so by this is actually quite narrow because of the pole. We know that poles actually produce narrow peaks. But then if you only have one zero to place, then in that case we know that zero actually creates attenuation. But where do we need the attenuation in a low pass filter? We need attenuation at the high frequencies. So then we place the zero at a high frequency. Okay, so now how do we get that? So at a high frequency we know that there is a sharp attenuation but then a broader peak. So this will actually produce a something like this, and then now here we have a broad one. So there is a difference. So with a single pole or a single zero we can achieve somewhat closer to an LP of a low pass filter, but then because of the properties of the system, magnetic response of a single pole and single zero, we get different types of the bandwidth basically. So zero causes sharp valleys and broad peaks, where poles cause sharp peaks and broad valleys. Right, so we just talked about it. So zero causes narrow valley, narrow sharp as a narrow, sharp valleys and broad peaks. Poles produce sharp peaks and broad valleys. Okay, so let's do the question number 3. A low pass filter realized using a single pole can provide excellent stop band attenuation. We just discussed about it, right? So a low pass, how do we get? And then fourth one is improved resonator. So improved resonator is actually where sorry, so the improved, okay, let's say okay, I need to talk about what improved resonator is. right? Question 3 is solve using the above, and then question 4. Okay, let's talk about the second order filters actually cause, so we have a 0, right? So we have two poles. Okay, so what we know is poles actually produce gain, and then we have two zeros here. So here there is a, so let's say this is like minus omega 1, and then this is omega 1, right? So we know that poles actually produce gains. So at minus omega 1, at omega 1, at plus omega, at minus omega 1 there is a pole, meaning there is a sharp peak in broad valley, and then at okay, let's do that with a different color. So sharp peak and a broad valley, and at omega 1 as well there is a broad valley and sharp peak. So this actually causes to shift the peaks. So basically now what we have is something like this. So the peaks have actually shifted. Similarly to the this side, right? So this is known as peak shifting. So the peaks do shift here. So the improved resonator is actually a system improved resonator is, and if you see the notes, we 1 minus z inverse 1 plus z inverse by 1 minus r e per j theta 1 minus r e per minus j theta. So basically we have zeros. Where are the zeros from the numerator? Can you tell me where the zeros are? So the zeros actually are on the unit circle. Okay, so two zeros and then two poles. So if we see here, we have a similar type of structure that we have talked about in the second order filters, right? So thus, so is there a peak shifting in improved resonator? Okay, now this is question 4. Then question 5, replacing z by z per l in the z domain, introduce l zeros between samples in the given time domain sequence. Replacing z by z power l, right? So let h of z, right? So let h of z is equal to some x of n z power minus n. right, from n equal to 0 to infinity. So here this will have minus x2 minus, sorry, not minus x2, x of minus 2, x of minus 1, x of 0, x of 1, x of 2, so on. Now replace z by z power l. So now what do we have? X of n z power minus ln. It's from n equal to 0 to infinity, right? So there are, so now what do we have? This will actually produce x of 0 and then 0 0 0, and then it will produce x of l, x of 2. Right, so yeah, I don't think I'll just move it. Find the structure. Okay, yeah, let's move on to question number 6 now. So multiple select questions. So it says that the following plot shows the log magnitude frequency response of a system with transfer function 1 by 1 minus r e power j theta z inverse. So basically this is, I mean, as I've shown the magnitude response of a pole. Basically this is what we are talking about, magnitude response of a pole. I mean, I've just discussed about it. Just write it down. What was that? H of z is 1 by r e power j omega into, sorry, j theta into z inverse, which is magnitude response of a system with single pole. Okay, yeah, so yes, so then the question number 8, sorry, I think this was question number 6, and then question number 7, which of the following corresponds to an improved resonator with center frequency pi by 2 and having magnitude response 1 by root 2 at omega equal to 4 pi by 9. So improved resonator with center frequency pi by 2 and magnitude response 1 by root 2 at omega equal to 4 pi by 9. So from the options, if we see, we can find that, so we have so actually substitute omega equal to 4 pi by 9 and check which system has magnitude equal to 1 by root 2. So then we narrow that down, and then center frequency pi by 2, right? Center frequency pi by 2, as I have said earlier, in the frequency response we know that if there are poles at locations omega 1 minus omega 1, we have a, what is the frequency, what is the center frequency here? So this is actually the frequency, the red one is actually the frequency response here. Sorry, something like this, right? So for sorry, this is what we have. We have improved here, so there sorry, okay, I'll just write down and remove it. If we have it like this, what we had was a shift in the frequency, but then this is what we had similar to it. So then the center frequency was somewhere in the middle. So and then now we need to find, we need that the center frequency is around frequency equal to pi by 2. So basically there should be, so it should be like this omega equal to pi by 2, meaning we can say that the poles are simply around like symmetric around omega equal to pi by 2, let's say. Okay, so according to this information, we can again narrow it down from the solutions and find which system actually has the center frequency at pi by 2. Okay, so this was question 7. And then question 8. So the input output relationship, output relationship is given by y of n is equal to 1 by 4 y of n minus 2 plus x of n, this 1 by 4 x of n minus 2, right? So okay, what is the question? So what will be the system output y of n? So what is y of n when x of n is equal to minus 1 power n? So x of z is equal to minus 1 power n z power minus n, right? So minus z yeah, minus z per minus n, so 1 by 1 plus z. Okay, 1 second, sorry. So minus 1 z inverse power n. So now it will be 1 by 1 plus z inverse. So this is x of z. Now from the system, if we do z transform, what we have, y of z is equal to 1 by 4 y of z z power minus 2 plus x of z plus 1 by z x of z z power minus 2. Now what do we get? So if we take y of z common, we get 1 plus 1 by 4 z power minus 2 is equal to x of z, if we take common, 1 plus 1 by 4. Oh yeah, actually yes, 1 minus, sorry, right. 1 second, I think the sound is pretty low. Yeah, so 1 minus 1 by 4 z power minus 2 by 1 plus 1 by 4 z power minus 2, right? So h of z is y of z by x of z, which is equal to, this is y of z into this, right? So 1 plus 1 by 4 z power minus 2 by 1 minus 1 by 4 z power minus 2. So now find y of z. So we have an x of n and h of a system with transfer function h of z, and then we have to find y of n. So I mean time domain h of n. So y of z will be x of z into h of z. We know x of z, we know h of z. Finally find y of z. So what you do is find y of z and then find y of n. Okay. Now ninth question is now another system with input output relation given by y of n equal to 1 by 8 of x of n minus 3 times x of n minus 1 plus 3 times x of n minus 2 minus x of n minus 3. So if we do z transform, what we have, y of z is equal to 1 by 8, let's say x of z common, so 1 minus 3 z inverse plus 3z plus 3 z power minus 2 minus z power minus 3. Okay, this is like, so if you see, let's say 1 is a and then z inverse is b, so a minus 3b 3ab, and then I think this is plus, right? Yeah, plus 3ab square minus b cube. So this is actually of the form a minus b whole cube. So if you see this form of the form a minus b whole cube, so you get y of z. So and then replace z equal to e power j omega, we get h e power j omega for the 9th question, right? In the 10th question, actually, I'll explain it right from here. So from the 10th question, it says that which of the following pole zero plots can be classified as a band pass filter. So what do we need in a band pass filter? So 1 second, maybe can explain it this way, right? So what do we need actually in a band pass filter is that we need something like attenuation. I mean attenuation at the low and the high frequencies, but then we need a gain at the middle frequencies. So basically what do we know? At the middle frequencies there should be poles, and then at the high and the low regions there should be zeros, right? So this is how we can say about that. So yeah, so that is how you actually find the, I mean, we can simply take what are the, I'll just write it down. Question 10, right? Question 10. So somewhere of this type it should be, right? So gain at the middle frequencies and then high attenuation at the low and high frequencies. So among the, so simply you can simply take like, superimpose the responses for single pole and 0 and see which is close to the above. Okay. Yeah. Okay. 1 second. Sorry. 1 second. Yeah. Okay, so the next is the last question. So let's say numerical answer h of n is -5 for n equal to 0 and 1 for n equal to 1. Okay. -5 for n equal to 0, 1 if for n equal to 1. Right, so then h of z will be -5 plus z inverse, right? And then find so h e per j omega will be -5 plus e per minus j omega. Find maximum of h e per j omega, which is maximum of -5 plus e per minus j omega. Okay. And then question 12 will be, consider a causal and stable system with input output relation given by y of n is equal to 0.5 y of n minus 1 plus 2 times x of n, right? And then 3 dB frequency. Okay, I'll just write it. Okay, so at 3 dB frequency, the magnitude of the magnitude of the response falls by 3 dB from the peak, basically. So if this is a low pass system, sorry, so if this is A in dB, right? So in dB, if this is A, this is A minus 3. It should fall by minus 3 dB, or it is basically 1 by root 2 from its peak value. Okay, so now the question is, so what we have is y of n is equal to x of n minus 1 by 2 x of n minus 1, which implies y of z is equal to 1 minus 1 by 2 z inverse x of z, right? So h of z, 1 second, so 2x of n now. sorry, this, one second, I think this is 2x of n, right? Yeah, yes, exactly, yeah. Oh, I think I've written it wrong, one second. I think I've copied it wrong, one second. So equation is y of n is equal to 0.5 y of n minus 1 plus 2 times x of n. So now it will be y of n. So if we do y of z is equal to 0.5 times y of z into z inverse plus 2 times x of z. Therefore h of z is actually 2 by 1 minus 0.5 z inverse. Yes, exactly. So this is actually in the form of a low pass filter, right? So with a pole, so there is a pole, I mean, you depending on the omega, right? So there is a pole actually at 0.5 at angle equal to 0, right? So it's like a pole at this point, meaning there is a peak at the zero, and then there is a broad valley. So this is similar to a low pass filter, exactly, right? So h e per j omega is 2 by 1 minus 0.5 e per minus j omega. Next, third is find maximum of mod h e per j omega, and find omega for which magnitude equal to 1 by root 2 times the peak value. This is the peak value. Okay, yeah, so I think this is the end of the assignment. So yes, so I have discussed some topics, and then talked about the assignment. So let me know if you have any doubts. If not, you can leave the session. Okay, thank you. No doubts, anything? Okay, yeah, yes. Okay, yeah, and then pole gives again, yeah. Hello, your voice is breaking actually. Hello, yeah, your voice is breaking. Yeah, sure. Hello, one second, can you talk again? Sorry. One second. I think no, 1 second. I mean, yeah. You are audible. But one second. So actually, it's not getting recorded. Yeah, can you talk? Yeah. You're audible. Yeah.
Yes,
Yes.
sir.
Go on. Yeah.
So actually, you were telling about the low pass filter, no, sir?
Yeah.
In question number 2.
Yes. One
So that
second.
is whatever you told for the poles and zero. So that is constant, sir. If we have the poles, we'll be having
Yeah. Yes.
high value at low frequency, and for zeros, will be at the high
So
frequency. We'll be
basically,
having the values.
a zero will, so zero at some angle and some magnitude, will actually create an attenuation at that particular frequency, right? So the here we have a zero at some angle r and some angle theta. So at that particular theta we have a attenuation, and then there is a, so depending on the distance from of the zero from the unit circle, this attenuation depends. Like if it is very near to the zero, then there is a very high attenuation.
Okay.
Okay.
If it is very near to the unit circle, the attenuation will be
Yeah,
more.
exactly. Yeah, even that is the case with pole. If the pole is getting nearer to the unit circle, then this actually, oh sorry, yeah, if the pole is getting nearer to the unit circle, then it is actually like very high
Mm.
peak for the pole as well. So depending on the so like r r e power j theta, this is the magnitude and angle. So this r as tending to 1, then depending on this pole or 0, it'll either go to 0 or it'll either go to infinity.
Okay, sir.
Yeah.
Yeah, okay.
Okay. Yeah. Any
So
other?
for the improved resonator,
Yes.
for a second order filter, we explained, right, sir?
Yeah.
Um,
Second order filter. Yes.
yeah.
Yeah.
So can you explain the graph once again, sir?
Yeah.
What you've explained here?
Yeah. Sure. So second order filter, right?
Yes, sir.
1 second. Second order filter. So let's say we have a pole pole zero plot of this sort where we have poles at r equal to j theta and r e power minus j theta. Right. So magnitude is same, but then angle is negation. Like so here theta and minus theta. Exactly. So now um, how will it be? So
So
this
the
pole. 1 second. So let me just draw it. Right. So omega 1 and sorry. So theta minus theta. So this pole will actually create a peak at that angle, right? So this will be somewhat like, sorry. Okay.
okay, sir.
Yeah, and then a pole at minus theta will
So
create.
due to that pole only, the peak occurs, right?
Yeah.
Due to that pole only, the peak occurs.
Yes.
Yes.
Yes. So
Okay.
now this, after adding these two, like this tail part is actually interfering with this part. So there is a peak, there is a shift in the peak. So finally, the actual magnitude will be somewhat of this sort. Okay. So
Mm.
so actually earlier these were the peaks.
Yes, sir.
So now these are the peaks. So there
It
is
is
a
got been
so
shifted.
there is a shift here.
Mm.
Right, so this is called shift. Peak gets shifted because of the interference from another pole. So as the poles actually grow farther apart, this interference decreases. Like when the poles are very near, the interference increases.
Okay. Uh-huh.
Right.
Okay. So once again, you tell me that when the poles are
For example, let's say the poles are now somewhere here and here.
okay.
Okay.
Mm.
So in that case, now the new uh, so minus theta 2 and theta 2. Right. So the new peak will be like of this sort, and then this will have this sort. So the interference, if you see,
Okay, okay, we'll be having more
yeah,
interference.
less interference.
Sorry, less interference.
Yeah.
Mm.
So if the poles grow farther and farther apart,
Mm.
the interference from another pole decreases. Right? Clear?
Okay, okay, sir.
Yeah. Is this topic clear?
Yeah.
Any other
So
doubt?
so
Yeah.
improved resonator means only
So
the peak shifting. Peak shifting is
I
called as
mean,
the
no. Basically, so this actually is the concept of peak shifting, but the improved resonator
ah
actually has two zeros at
two
this.
zeros and two poles.
Yeah,
Okay.
two zeros here. So because of two zeros, this is
Mm.
at the uh, 1 second. So this is at the low frequency, and this is at the high
Mm.
frequency. So
Mm.
because of improved resonator, there is an attenuation at low and high frequencies,
Yeah. Mhm.
right?
Okay.
Yeah. So because of, so let's say the poles are not there.
Mm.
Okay. So now we only have two zeros.
Mm.
Okay. Only two zeros. Then what will the plot look like? So what will a zero do? It will create attenuation, right?
Yes, sir.
So attenuation,
Mhm.
so it will be very low.
Very low.
Yeah. So it will be very, it will be peak, like narrow low, right? So zero creates a narrow valley. So
Mm.
narrow one and something of, sorry, uh, a narrow one. And then at angle pi also there is a very narrow narrow, and it grows like this. Okay, so this is a resonator. So now we add two more poles here. So when we add two more poles in between, this will actually create some more grain,
Yes, sir.
right? So now we'll have even more valley, like a sharp valley and a high gain in the middle frequencies,
Mm.
right? So this is the improvement. So because we have added the poles here, there is an improvement in the gain in the actual band pass region.
Okay. Okay. Mm.
Get it?
Okay, sir.
Yeah, so that is why it is called improved resonator. So if
Okay.
there are only two zeros, it is a resonator. Now we
Yes, sir.
have two more zero. We are
Two
improving it.
more. Okay.
Yeah,
The
so
gain has
it's
been
an improved
increased.
resonator. So I mean, I taught this concept because I wanted to explain how the peak shifting happens.
Okay. Okay, sir.
Okay.
Mm.
Yeah.
Okay, sir. So here in the fifth question, sir.
Okay.
So yeah, we need to replace z is equal to z power l.
Yes.
Okay. So the limit is from 0 to infinity. So we'll be having only the causal values, right? In the only in the positive value we'll be having, right, sir?
Yeah. I mean, I wrote it here. Actually, it is. I mean, did they actually mention it in the question? So they did not mention any causal. I mean, in the like that. So it should actually be minus infinity to infinity. It's my mistake. Minus infinity to infinity. Yeah.
Okay. So minus infinity to plus infinity means you'll be having both the values. From minus
Yes.
to plus
Yes.
infinity, you'll be having the values.
Exactly.
And if you're going to substitute z is equal to z power l,
Now we have
so
z power minus l here.
um,
So it's like only for the values of z l n, the
l,
multiples of l, there is a non-zero value.
yeah, with respect to the value of l only, our value changes, right, sir?
Yeah. So let's say l equal
Otherwise,
to,
we'll be mm,
so let's say l equal to 5. So for n equal to 0, it is z per 0. So we only have coefficients for 0. I mean z per 0, z per minus 5, z per plus 5, z per minus 10, z per plus 10,
mm,
like that.
mm, mm. Okay.
Yeah.
Okay. So, so it depends upon the value of L only, the
Yeah.
Z transform values.
Yes. Yes.
Actually, this pole zero concept it's a vast, I think. So, actually, this I have taken DSP many times, but
Okay.
I am learning new topics now. I've got regarding the design of filters.
Yes, yes,
Actually, it
exactly.
is new to me, sir.
Yeah, yeah, yeah. I understand. I mean, the
Actually, we haven't studied like this. Sir. Just we will be saying it's a poles and zeros. We'll be having the low pass filter like this and high pass. So
mm,
we'll be substituting the formulas.
yeah,
But this
exactly.
many concept is there is means this is the first
I
time.
mean, so like this
So
is
it is.
actually a very, like if you see, it's a really really interesting and beautiful topic. Like, let's say, I mean, you only need a low pass filter. Let's say, so you can create that low pass filter with either a single pole or a single zero. And then for if you use a single pole, you have a narrow peak and the broad valley. But if you want a single zero, you'll have a broad peak and a narrow valley. So once if you know the uh, properties of the response, I mean how the response is when for a single pole and a single zero, you can find for any number of poles and zeros. Basically, you just have to superimpose all of them and find the final magnetic response, right?
I think this system is a vast topic, right?
Yeah, kind of, yeah, but it's, I mean, it's really like
If we
it's
understand this basic concept, you can do it for
mm,
any number of poles and zeros.
exactly, exactly. I mean, like, so how the poles and zeros, why first in the first case, why Z transform was introduced, and like how poles and zeros. So we know that DTFT means that z equal to 1. I mean, if you put z equal to
Mm.
1, mod of z equal to 1, you get the DTFT. And then why do
Yes.
we care about all other values of z? So now we see it is evident that the locations of poles and zeros are actually important. Like here,
Yeah.
the pole is getting to 1, the peak is actually going to infinity,
I.
and then when zeros is
Infinite.
going to unit magnitude, then the valley, the particular valley is actually going to 0, right? So yeah, so that is where the pole zero plots, and also you talk about stability of the systems, how inverse of a system works, and then you talk about this minimum phase systems, right? You say that all poles and zeros are inside the
Inside the unit
unit
circle,
circle.
it will be a stable
Yeah,
system like that.
yes, yes, yes. All these concepts, I mean, when the actual filters are designed, and like in the no, I mean, there is one more example where, like, what can be created with both poles and zeros. So there is an example in notes. It says that, one second, let me just open that up maybe. um, One second.
Yes.
Yeah, so like, so okay, and then we have two zeros, pole zero plots, and we have a system where there are only a few zeros, like only here, and then there are poles. Okay, like three, four poles, and then five zeros. This filter, I mean, if we want to consider only poles, like if we want an FIR filter, we don't have any poles, right? So in that case, the pole zero plot should actually contain like so many zeros. So basically a 32 order zero, like FIR system zeros, is almost equivalent to having both poles and zeros with very less number of poles and zeros, right? So the frequency response generated by this and this is actually similar. No, I mean, not exactly same, but similar. So this is like a low pass filter basically, right? So but what poles here give is the enhancement of the gain, right? So whenever there is a pole, we know that there is a gain in that particular frequency, right? So that is what. So this is the really nice concept. If you see, like, if you can add poles, then we are getting a gain here. So 32 order,
Gainers.
yeah, this is a 32 order system, and this is just a 7, I mean, 5 zeros and 4 non-zeros basically. But then this is IAR system, and this is an SFIR system. Yeah, so this is like some really nice and interesting topics that we can learn from Z transforms. Yeah, I mean, you'll get to it slowly. Just go through the lecture notes; they are actually quite clear.
Mm.
I mean, you can let us know any if you have any doubts in the next session, or you can add in the discussion forum as well, right? So this is quite important and interesting topics to read actually.
Mm.
This OpenM Schaefer book actually has a really nice,
Open in. Oh, oh,
yeah,
that's okay.
OpenM
Mm.
book has actually like explains it really well. Maybe you can go through that as well.
Okay, sir.
Yes.
Okay.
Okay. Yeah.
Thank you. Thank you so
Yeah.
much, sir.
Sure. Sure. No problem. Okay. Thank you.
Thank you, sir.
Thank you. Thank you.